Hello, everyone. Just going to give a quick example to highlight a little bit about the distinctions between vector data resolution and raster data resolution, and also how you can convert between, say, points, lines to polygons, and then converting between vector to raster back to vector, for instance. So I'm just zoomed in on Trout Lake in Vancouver. For those of you who aren't particularly familiar with where that is, it's just a park in East Vancouver. And so currently here I've got a set of 5 points, which I have digitized manually around the boundaries of Trout Lake. And so we're going to try to represent this lake and see how we can do representing it with a very low resolution set of points, right? We've only got 5 points to represent this lake. Now you see that I've put them in the corners so that it might work out okay. So I've got this model here. And what this model is doing is we're just converting points to a line using this tool. And then we're also converting points to a polygon using 2 steps. And so the only difference between these two is that in this one, we're just running it with the defaults as is. And this one, I've selected a feature close line. So again, we've got these points. I'm going to run this model and convert to a open line, a closed line, and then also the closed line is going to get converted to a polygon. So I'm just going to click run. This will take just a second. And it is done. So first, let's add this to the display. And see, this is what the open line looks like. And so the way this tool works is that unless you have another attribute to specify by, it just goes in order that the points were added to the file. So this open line is just following the direction in which I added this point, then this point, then this point, dot, dot, dot. Now the closed line looks a little bit different. So you can see that it connects fully. So this is open and this is closed. And so by definition, to make a polygon, the starting point and the end point have to be the same. So in this case, that's right here, right? So you can't make a polygon with this line, but you can with this one. And so that's what this featured polygon tool does. And so this is the resulting estimate, if you will, or approximation of the boundaries of Trout Lake using 5 vertices. So this is a very low resolution approximation of the lake, right? You can see that it gets the overall shape okay, but it doesn't, get these areas, for instance. It doesn't account for a lot of stuff. So let's double the resolution. I'm going to create a new feature class, a new set of points. We'll just call it 10 points. And so this one's just going to have 10 points, or double the resolution, if you will. And so this will yield a closer approximation to the area of Trout Lake, if you will. So we've got this 10 points here. And if I go to edit and just add, I can create feature on 10 point. So I will use every vertice or every vertex in the 5-point layer, but then I will put a new point in between each to do a better job of approximating the coastline, if you will. So we'll kind of split the difference between each point to get a higher resolution approximation of the lake's shoreline. Now, this is still only 10 points, you can see that this lake has, an undulating coast. This is not going to be a perfect approximation either, but it will yield a closer approximation because we have higher resolution, greater number of points creating that polygon. So I have saved this layer. And so now if I take the 5 points out of the model and instead rerun everything with the 10 points layer, we can compare and see how different things look, right? So currently, this is the polygon that we have, and this is the line that we have. You can run it and see the ensuing result. And so you can see that this polygon still not perfect, right? Doesn't quite get down here or down here, and there's some areas that are, say, perhaps labeled as lake that aren't. But it's a much closer approximation to the actual area of Trout Lake, and that is because we've increased the resolution. We've doubled the number of points we're using to represent it. So now I'm going to open another model. And so this one is going to do a couple of things. First, I just want to convert a raster to a polygon to show a little bit of examples about how raster resolution compares to vector resolution. So vector resolution is just determined by the number of vertices that we have in this polygon, right? So these points here. Raster resolution is instead determined by a cell size. So first, we're just going to run this step with a cell size of 10. Now, this whole string of models I will show in a moment. What this is doing is it's converting from a vector to a raster, back to a vector, back to a raster, and then back to a polygon again. And so the point of this is just to highlight that error will cascade when you repeatedly convert between data types. It's okay to convert once, maybe twice, but generally speaking, you don't want to just do it iteratively over and over. But we won't go that far yet. For now, I'm just going to run this at 10 meters and compare the resulting output. And so this is the raster result that you get. You can see, just kind of looking, that it doesn't quite match up perfectly, right? And so it doesn't mirror the line that we have perfectly. It does a decent approximation. Now, what if we change the resolution of this to, say, 20? So changing the resolution of this raster to 20 is going to decrease the size or the number of cells in the raster image by increasing the overall size of a given cell. And so what this does is it means that it takes up less storage space, but it also means that it gets a grainier or coarser approximation of the lake. So let's change it again, say 50, right? And so this is getting to where it's not too much smaller than the actual lake itself. We'll see what that does. So this is a very, very rough, coarse approximation. It's not doing a very good job. That said, this file size of this image is smaller than using the large file size, or a high resolution raster image with a smaller cell. Now, conversely, we can change this to, say, 1 meter and run it. And we'll get a very close approximation for the actual lake area, or the actual polygon area, sorry, right? And so this really closely matches this. But the thing is, with the small cell size, it means it takes a larger number of cells to store that. And so we need a higher resolution raster to make this approximation. So the moral of the story is that when you're representing spatially homogeneous features like a lake or something, it's generally better, easier, more efficient to use a vector image, because in order to get the same equivalent resolution with a raster image, you need a larger data set, right? So we can get a pretty good approximation of this lake with just a polygon that has 10 vertices. But to get the equivalent representation with a raster, you need a whole bunch of cells with 1 meter cell size. So another thing that this model is doing, again, is converting to and from. So we're going polygon to raster, and then raster back to polygon to get this, and then converting again. And so going back to a polygon. And so what I'm going to do is go through this series of events, and then I'm going to compare the area of the output of this multi-conversion step to the original area of this polygon to show that error will cascade, right? And so that choice will also be dependent on resolution. So currently the rasters are set to 10 meters resolution. So we'll run it and see, we'll run the full model and see what we get. All right. So this was our initial input, and this is the final result that we get. I'll change this color scheme so that it's a little easier to distinguish. So it's the original, and this is the end result. And so if we make some multiple conversion steps, that's how it's going to go. Now this is the in between, right? And so you can see that one doesn't match either. And so when we even just do it once, polygon to raster, back to polygon, we end up creating some error. And so you can look at the attribute table, look at the area to see how that works, right? So this is the shape area of the original. Versus the shape area of the converted and then reconverted, right? And so they're not immensely different, but the area does differ by about 140 square meters. Then we open this one. And we see, again, they are not equivalent. And so this highlights that when you convert between data types every single time, you cause error. Now, if you use a higher resolution raster approximation, so you set this cell size to 1, and you set, well, we'll just run this one step. Do the conversion once. If you use a 1 meter resolution raster, you see that we get a much, much closer approximation. You can barely even tell visually that there's any difference at all. Now, if we open the attribute table, we do see that there is still some difference, right? But it's only on the order of about 20 square meters versus 100 square meters plus, like the last one was. Now we can go in the other direction and say, what impact does a huge cell size have? Say change that to 50 and run again. So we see that this creates a really, really bad approximation, right? So again, highlighting the real mismatch here when you use, like, say, poor quality or poor resolution raster data and try and convert between data types, right? So there's a really, really far off approximation, for instance. So one other thing you can play around with is, say, how specifically to convert the polygon. So convert from raster to polygon. So by default, ARC is going to simplify these polygons, but if you don't do that and you run this, you turn that simplification off, you're going to end up with a very different result again. And so you end up with a polygon that just matches the original raster image, right? So there's lots of different ways you can convert between data types, lots of choices you can make. Each choice will induce some degree of error depending on how you go about it.